A very good morning, students. Welcome to science session for class 9, and today we are going to see unit 3 fluids. And now in this lesson we are going to see what is meant by thrust, pressure in liquids, what is atmospheric pressure, what is meant by Pascal's law, density, and about the new term buoyancy, Archimedes Principle, and law of floatation. Let's go into the session, children. A very good morning, students. Welcome to science session for class 9, and today we are going to see unit 3 fluids. And now in this lesson we are going to see what is meant by thrust, pressure in liquids, what is atmospheric pressure, what is meant by Pascal's law, density, and about the new term buoyancy, Archimedes Principle, and law of floatation. Let's go into the session, children. Now first let us understand what is fluid. Now what do you mean by fluid, children? Now we know that there are three states of substances, isn't it? Now one is the solid, the other one is liquid, and gas. So these are the three states of the substances. Now what is fluid? Now which of these substances comes under fluid? So fluid is anything that flows, isn't it? Now any substances which flows comes under the name fluid. Now we can say that the gases and the liquids comes under fluids. So now for example, you can see the picture, you can see the water, milk, honey. So all these are the fluids. These are the liquids that flows, isn't it? And even gas flows. So gases and liquids comes under fluids. Now we said that anything that flows is a liquid, and we also said that gases and the liquids comes under fluids. So now gases and liquids have few similar characteristics, isn't it? Now both the gases and the liquids have substances or the molecules that is present are in the relative motion, right? So these fluids, that is the gases and the liquids, consist of the molecules which are in the motion. So in general we can say that the fluid is any substance in which the molecules are in random motion. Now for example, if you take the glass of water, now water contains water molecules, isn't it? And these water molecules are continuously moving. They are in relative motion. So this is how the molecules in the fluids are. So the molecules in the fluids are in relative motion. So when the molecules are in relative motion, they collide with one another, isn't it? And they also collide with the container. So like the solids, fluids also have weight, isn't it? And therefore it exerts pressure. Now for example, if you take the container filled with the water, when filled in a container, now what happens? The pressure of the fluid is exerted in all the direction, isn't it? Because it is in relative motion, and at all the points of the fluid, at each and every point of the fluid, the pressure is exerted in all the direction because it collides with one another, and it also makes the collision with the walls of the container. Now since the molecules of the fluid are in constant rapid motion, the particles, what will happen? It will move equally in all the direction. Therefore it exerts the pressure in all the direction. So here we are going to learn about what is pressure and what is thrust before we go into pressure in liquids. Now look into the screen, children. First we'll understand what is thrust. Thrust is nothing but the force that is applied on the surface in the direction perpendicular to the surface. Now look into the picture. Now here we are pushing a pin by its pointed end, isn't it? Now here a force is applied, but it is perpendicular to the surface on which it is applied, right? So thrust is nothing but the force, but it acts perpendicular to the surface on which it is applied. Now since it is a force, it has the unit as same as that of the force. So the SI unit of thrust is Newton. Now, first let me give you two examples. Now for example, if you stand on and loose sand, now what happens? Your feet goes deep into the sand, isn't it? Now when you lie on the sand, what will happen? You won't go deep into the sand, isn't it? So the force that is exerted on the sand is the weight of your body, isn't it? The force, that is F is equal to m into g. Now this force is acting perpendicular to the surface, and that is called as thrust. Now just now we said that the force acting perpendicular to the surface is the thrust. So when you stand on the loose sand, the force acting on the area is equal to the area of your feet, isn't it? Yes. Now when you lie down, the same force act on the area of your whole body, and here the area is large, isn't it? So thrust per unit area is nothing but the pressure. So pressure is defined as the effect of the thrust per unit area, or you can say the force per unit area acting on a body is called as pressure. Now what will be the formula for pressure? Pressure is equal to thrust divided by area. Now what is the SI unit? The SI unit can be Newton, because thrust is measured in Newton. So Newton divided by area in meter square. So unit of pressure is Newton by meter square. Or the other unit that is measured is Pascal. So it is denoted by PA. So 1 PA is equal to 1 Newton divided by 1 meter square. Now let's understand the relationship between the pressure and the area with the examples. Now look into the screen, children. So what you're going to do, you're going to take a pencil, keep it in between the thumb and your index finger. You can see it is given in the picture, and you're going to hold it for some time. You're going to give pressure using your thumb and the index finger. Now you are going to apply equal force from both the ends towards the pencil for few seconds. Now what will happen after you take the pencil? You can see a depression is on your thumb and the index finger. Now look into this picture, children. Now how is the depression in your thumb and the index finger? Do you find any difference? Yes, of course. There will be more depression on your index finger, and there will be an less depression on your thumb. Now why is it so? This is because the pointed end of the pencil has lesser area and the other hand has the more area. So when there is a less area, the pressure applied will be more, and when there is a more area, the pressure applied will be less. So pressure and area are inversely proportional. If the area is large, the pressure is low, and if the area is small, the pressure is more, and you can see more depression on your index finger than on your thumb. Now look into this example, children. So when you stand on the loose sand, now what will happen? Your feet goes into the sand, isn't it? Now when you lie down on the sand, you don't go deep into the sand, isn't it? So here the force exerted in both the cases is your weight of the body, isn't it? That is F is equal to mg. The weight of your body is the force that is exerted in both the cases. That is, in the case if you stand on the loose sand, or in the other case if you lie on the sand. Now look into this picture, children. Here more pressure is applied when you stand on the loose sand, because the area covered by your feet is less. So since the area is less, more pressure is applied and your leg goes deep into the sand. Now here when you lie down, the area is more, isn't it? When there is a more area, less pressure, so the depth is much lesser. So look into the picture, children. Here pressure is nothing but the force by area, and here the pressure, and here we call the force that is acting perpendicular to the surface is called as the thrust. So pressure is equal to thrust divided by area. Now just now we saw, isn't it? So pressure is equal to thrust by area. So when a constant force is applied, when a constant thrust is applied perpendicular to the surface, then the pressure is inversely proportional to the area. Now you can see the picture, isn't it? More area, less pressure, and if it is in less area, more pressure. So pressure is inversely proportional to the area. So the pressure depends on two factors. One is the force, the other one is the area. Now, how is the force related to the pressure? It is directly proportional. More force, more pressure. If there is a less force applied, then there will be a less pressure. Now, how is the area related? Area is inversely proportional to the pressure. More area, less pressure. If there is less area, more pressure. So look into the picture, children. Here you can see two containers, one containing the liquid, the other containing the gas, isn't it? Now here having said that the gas and the liquids are the fluids, and we also said that the molecules that is present in this fluids move in constant and rapid motion. So the particles are in constant motion. So since they are in constant motion, they exert pressure in all the direction. And we also said that the liquid pressure is equal to total force exerted by the liquid divided by the area over which the force is exerted, isn't it? So pressure, that is liquid pressure, is equal to force divided by area. Here we are going to see pressure due to liquids, that is the fluids. Now see the first case. Now the force exerted due to the pressure when a body is immersed into it. Now you can see the first picture in which the body is immersed into it, isn't it? Now it exerts pressure on the walls of the container and it is perpendicular to the surface, isn't it? Now here the force is acting in all the direction. You can see the arrow mark, isn't it? The force is acting in all the direction. Now look into the second picture, children. Now when you push or immerse the balloon that is filled with air, now what happens? After sometimes it immediately comes out and floats on the surface of the water, isn't it? Now this shows that water exerts pressure in the upward direction. Now here we are talking about the pressure due to the liquid, that is the water here, right? So what happens? The water exerts a pressure in the upward direction due to which the balloon comes to the surface and floats on the water. Now look into the third picture, children. That is a bottle containing water and it is pierced, isn't it, in all the direction. Now the liquid pressure acts in the lateral sides, that is on the walls, with the walls of the container. Now when the bottle is having a water, right, and if it is pierced on the sides, pierce it with the pin on the sides. Now what you can see the water coming out with a great speed in all the direction, isn't it? So this is because the liquid exerts pressure on the walls of the container, so it comes out of the bottle with the pressure. Now look into this picture, children. Here you can see two containers, one containing water, the other containing the cooking oil, right? Now if you make a hole in two containers at the same level, at the same height, now what will happen? You can see that the water is coming out, forcing out from the containers, isn't it? Water is coming out with more pressure than the cooking oil, isn't it? So this indicates that the pressure depends upon the density of the liquid. Now if you compare the density of the two liquids, water and the cooking oil, water is less denser and the cooking oil is more denser, isn't it? So it is coming out with a greater force, and the cooking oil being more denser, the force is less. Now look into this picture, children. Here this activity explains how the pressure depends upon the depth. Now here you can see a plastic container and you are making holes with the nails in a vertical column from top to bottom. Now you are making three holes, one at the top and the other in the middle and the last at the bottom of the container with a little height. Now if you fill the can with the water, now what will happen? Now here you can compare the speed of the water. Now water will drip out from the top hole. Now if you see at the middle hole, now it will come with a little increased speed. That is at the bottom hole, you can see that the water comes out with more pressure, right? So at the top, right, if the height is more, the water will drips out from the top hole. Now there will be a little more speed compared to that of the first hole, and at the bottom the water comes out with more pressure. So this indicates that the pressure exerted by a liquid is determined by the depth, or depends on the depth. So on the whole, we can say that the factors determining the liquid pressure in liquids is depth, density of the liquid, that is rho, and acceleration due to gravity, g. Now we are going to derive the pressure due to the liquid column. Now for that we are going to take an wider container which consists of the water, and in this wider container we are going to consider only this liquid column, and we are going to derive the pressure due to this liquid column. Now here let the area covered by the liquid column be A and the height of the liquid be H. Now here the volume that is contained in the liquid be V. Now we know that the thrust at the bottom of the liquid is equal to the weight of the liquid, that is weight of the column, isn't it? So F is equal to weight of the liquid, and we also know that F is equal to m into g, mass into acceleration due to gravity. Let this equation be 1. Now we know the formula for the density, isn't it? So density is equal to mass by volume. Now I have substituted density as rho, right? The symbol for density is rho, isn't it? So mass is represented by m and volume by v. So rho is equal to m by v, and I am bringing this v to this side. So m is equal to rho into v. Now let this equation be 2. Now here we are going to calculate the volume of the liquid column. Now volume of the liquid column is equal to area into the height. The area into the height will give you the volume of the liquid column, isn't it? So V is equal to A into H. So that will give you the volume of the liquid column. Now I am going to substitute this V is equal to A into H in equation 2. Here we have derived m is equal to rho into V, isn't it? Now I'm going to substitute here. So m is equal to rho, instead of V, A into H. Now I'm going to substitute this m is equal to rho AH in equation 1. So what is the equation 1? F is equal to m into g. Now F is equal to m into g. Instead of m, I'm going to substitute rho AH, isn't it? So that will become rho AH into g. We know the formula for pressure, isn't it? So P is equal to F by A. Instead of S, I can substitute this, isn't it? So F is equal to rho AHG, isn't it? So I can substitute here. So rho AHG divided by A is nothing but the area. Now I can cancel A in the numerator and the denominator, isn't it? So when I cancel, now what will I get? P is equal to rho HG, isn't it? So P is equal to rho Hg is the pressure due to the liquid column. So the pressure due to the liquid column P is equal to H rho G. So we can say that the pressure due to the liquid column depends upon the depth H, density rho, and acceleration due to gravity. So pressure due to the liquid column P is equal to H rho G is an important equation and important derivation, and we will use this formula, that is P is equal to rho Hg, in few numerical problems that is given in your solved problems and also in the book back numerical problems. So see to that you learn this derivation. You can copy this derivation in your classwork, children, and be thorough with this derivation. Now let's see what is atmospheric pressure. Now we know that the earth is surrounded by a layer of air, isn't it? The layer of air that surrounds the earth is called as the atmosphere. Now we also know that the air occupies space and has mass, isn't it? So since it is a matter, since it occupies space and mass, it exerts the pressure. So the pressure that is exerted by the atmosphere is called as the atmospheric pressure. And now here we are going to consider that the atmospheric pressure acts as in column, right? So the atmosphere acts as in column. We are going to consider a column of atmosphere, and we are going to compare the air pressure and the density at a higher altitude and at the sea level. Now consider this column. Now at the sea level, what happens? There is a taller column of atmosphere, isn't it? Now here the taller column pushes more pressure or exerts more pressure, isn't it? No. So since it exerts more pressure, the air pressure and the density are higher at the sea level since the column is more. Now on the other hand, considered at the higher altitude, right? Now at the higher altitude, what happens? The column is short. Consider that you are at the top of the mountain. Now the column that is present above the mountain is short, isn't it? So the pressure that it creates will be less. So the air pressure and the density are lower at a higher altitude. Altitude in the sense height. And we also know that the air gets thinner and thinner with increase in the height, increase in the altitude, isn't it? So the atmospheric pressure decreases when we go up into the mountain. Now on the other hand, what happens? The air becomes heavier, isn't it? So for example, when you go deep into the mines, what will happen? When you go deep below the sea level, the air becomes heavier and the air pressure and the density will be heavier at the sea level and below the sea level, like mines. Now we are going to see the measurement of atmospheric pressure. Now how is the atmospheric pressure measured? Now there is an instrument that is used to measure the atmospheric pressure, and that is called as barometer. Now here you can see a mercury barometer. This was first designed by an Italian physicist, that is Torricelli. This consists of a tub containing mercury and an long glass tube. And now this long glass tube is turned upside down into the container containing mercury, and this is done by closing the open end of the glass tube with the thumb, and it is immersed into the container containing mercury, and the thumb is released after it is immersed completely into the tub containing mercury, and care should be taken that no air bubbles enters into the glass tube. Now let's see how does this barometer works. The barometer works by balancing the mercury in the glass tube with the atmospheric pressure, that is outside atmospheric pressure. Now consider you have less atmospheric pressure, AP. What is AP? Atmospheric pressure. So the outside atmospheric pressure is less, or you can say low atmospheric pressure. Now what will happen if there is an decrease in the atmospheric pressure? More and more of mercury drains into the tub. That is, from the mercury column, more and more of mercury will drain into the tub. Now consider the other case. If the atmospheric pressure is high, that is the outside pressure, that is atmospheric pressure is high, it is increased, right? Now what will happen? It pushes more of the mercury into the tube. That is, the mercury from the tub enters into the glass tube, isn't it? And you can see that it increases in the glass tube, that is in the column, right? And care should be taken that there is no air trapped into the space between the mercury and the closed end. There is a vacuum at that space, that is at the bottom, isn't it? And this vacuum will not exert any pressure, isn't it? So the level of the mercury in the tube provides an precise, accurate measure of the atmospheric pressure. Now this type of instrument can be used in labs or in the weather stations. Next we are going to see what is Pascal's law. Now this law is named after the scientist Blaise Pascal, who is a French mathematician, and he gave a law which is called as the Pascal's law. Now to understand Pascal's law, now let us consider an experiment, right? Now here this activity consists of a round bottom flask fitted with a piston. Here you can see the piston P, so that the pressure is applied from the upward direction. Now this flask contains holes over its surfaces and it is filled with water. Now when the pressure is applied from the top, that is from the piston, now what will happen? This pressure is uniformly transmitted throughout the liquid, and the liquid that is coming out of the holes will have equal pressure. So this law states that the external pressure that is applied on an incompressible liquid is transmitted uniformly throughout the liquid. So this principle is applied in various machines in our daily life. Next, we'll see the applications of the Pascal's law, that is hydraulic press. Now, the Pascal's law becomes the basis of the important machines that is developed, and one of the machine is the hydraulic press, right? And now this consists of two cylinder. Now here you can see that it consists of two cylinder of different area of cross section. One is A1, which has the lesser area of cross section, and A2, which has large area of cross section. Now these two cylinders are fitted with the piston P. Now the force F1 is applied on the small cross section area, and it is in the downward direction. What will happen? We said that according to Pascal's law, when the pressure is applied, it is transmitted uniformly throughout the liquid, isn't it? So the pressure P that produced by the small piston is transmitted equally to the large piston, but in the upward direction. Now this will produce the force F2, and the force that is produced F2 will be much larger than that of F1. And we can also calculate the pressure on the piston of the smaller area, and we know that the pressure is equal to force divided by area, isn't it? Now we can calculate the pressure on the piston of the area A. That is, for example, the force applied by F1 on the area A1. Now here the pressure is P is equal to F1 divided by A1. Now similarly we can calculate the pressure large piston, isn't it? So P is equal to F2 divided by A2. Now when you compare these two equations, we also said that the pressure is equally transmitted. So we can write F1 divided by A1 is equal to F2 divided by A2. Now you can calculate what is F2 using this equation. So F2 is equal to F1 into A2 divided by A1. And look into the picture, children. Here you can see the automobile hydraulic lift, isn't it? Where the heavy vehicles are lifted. No, so this is one of the application of the Pascal's law, that is hydraulic press. Now here you can see that the pressure is exerted in the smaller cylinder using a compressor. The pressure is exerted equally in all the direction, isn't it, according to Pascal's law. So what happens? It exerts over a large area on the other side, and the heavy vehicles get lifted. So a small force exert over a long distance give rise to a multiple force that lifts the car. Next we'll go to density. Now consider the two round bottom flask, one containing 200 ml of kerosene, the other containing 200 ml of water. Now we are going to measure the weight in a balance. The flask filled with water will be heavier than the one filled with kerosene. Now why is it so? Now you can see the weight, isn't it? Now here you can see that 280 grams of kerosene and water is 330 grams. Now if you consider the weight of the flask to be 80, now you can subtract 80 from each of the weight. So the weight of the kerosene will be 200 and that of the water will be 250. Why is the flask filled with water is heavier? Now this is because of density. Now to understand density, let's make a small calculation. Now we are going to calculate the mass per unit volume. Now if you consider the mass per unit volume, we know that the mass of the kerosene is 200. Now volume is 250. So 200 by 250 and this will give 0.8. Now if you consider water, now we said that the weight of the water is excluding the flask, it will be 250. So the volume is 250. So 250 divided by 250, 1 g per centimeter cube. There is a difference, though the volume that is occupied by the water and the kerosene in the round bottom flask is same, but there is a difference in the weight. So this is nothing but density. So density of a substance is mass per unit volume. So density of any substance is mass per unit volume. And here the density of the water is 1 grams per centimeter cube, and that of kerosene is 0.8 centimeter cube. So the SI unit of density is kg per meter cube, and if you are giving in grams per centimeter, it is grams per centimeter cube. The symbol of the density is rho. Now let's see the relative density. Now the relative density, in the sense we are comparing the density of the two substances. Now we are taking the density of the water to be the standard substance, that is density of the water at 4 degrees C as a standard substance, and we are going to compare the density of the other substances. Now for that we use a formula. Relative density is equal to mass of certain volume of substances divided by mass of equal volume of water at 4 degrees C. So this will give you the relative density. Since the relative density is the ratio of mass of given volume divided by the mass of equal volume of water, this doesn't have unit. There is no unit for relative density. So the formula is relative density is equal to mass of certain volume of any substances divided by mass of equal volume of water at 4 degrees C. Now let's talk about floating and sinking. When does a substance float and when does it sink? Now, whether an object will sink or float, that is determined by the density. Now we were talking about the density and the relative density, isn't it? An object will sink or float depending upon the density of the object and the density of the liquid. So here we are going to compare the density of the object with that of the liquid, and we are going to determine whether the object will float or sink. Now consider the first case. Now, if the density of the substance is more than the water, now what will happen? It will sink at the bottom. Now, for example, stone. Now, if the density of the stone is more than that of the water, it sinks in the water. Now, on the other hand, if the density of a substance is less than the density of the water, it will float at the surface of the water. Now for example, if I take a piece of wood which is less denser than water, then what will happen? It will float on the surface of the water. So the floating and the sinking of the substance is determined by the relative density, that is the density of the object compared to that of the density of the liquid. Next we are going to see about the hydrometer. Now hydrometer consists of a cylindrical stem having a spherical bulb at its lower end and a narrow tube at its upper end. Here you can see the spherical bulb at its lower end and a narrow tube at the upper end, you can say, and the lower spherical end, now it is partially filled with the lead shots, or you can say it is filled with mercury. Now here you can see it is here, it is the lower end, isn't it? It is filled with the lead shots or it is filled with mercury. This lead shots or the mercury helps the hydrometer to float or stand vertically in the liquids. Now normally what happens? It will tilt towards the walls of the container, isn't it? Now stand vertically in the liquid, these lead shots or the mercury helps. Now this narrow tube has the marking so that the direct reading of the relative density or the density can be measured. Now here the liquid to be tested should be poured into the glass jar. Now the hydrometer will be gently dropped into the liquid whose density or the relative density has to be measured. Now what will happen? It will float, isn't it? The hydrometer will float freely in the liquid, isn't it? Now the reading against the level of the liquid touching the tube gives you the relative density. Now here you can see the reading, isn't it? Now using this you can find out the relative density of the liquid. Now hydrometers will be calibrated for different instruments such as lactometers for measuring the density of the milk. Now if you take sacrometers that is used for measuring the density of the sugars in the liquid, alcoholometer for measuring the alcohols that is present in the spirits. Now, if you see the lactometer, it is one form of the hydrometer that is used to check the purity of the milk, and this is based on the principle of the gravity of the milk. Okay. Now, this will also consist of a long graduated tube with the cylindrical bulb at the lower end, and this will also have the graduations starting from 15 at the top, and when you come down it will range up to 45 at the bottom. Now, this tube is filled with air. Now, what will happen? This air chamber causes the instrument to float, isn't it? Now, this spherical bulb that is filled with mercury, this will makes the lactometer to sink in a proper level, isn't it? And it will float upright, that is vertical in the milk. Now, inside the lactometer there will be a thermometer that is extending from the bulb. Now, here you don't have in the hydrometer, but in the lactometer you will have a thermometer that is extending from the upper bulb. Now, here you have the narrow upper part, isn't it? Now, there you have a thermometer. Now, why is the thermometer present in the lactometer? Because the correct lactometer reading will be obtained only at a temperature of 600 degree Fahrenheit. So, the lactometer measures the cream content of the milk, or you can say the density of the milk. So, the average reading of a normal milk is 35. So, lower the cream, higher is the lactometer floats in the milk, and more the cream, lower is the lactometer floats in the milk. Now, next we'll go to what is buoyancy. Now, consider when an object is immersed in the liquid, now what will happen? It will displace the same amount of the liquid, or you can say same weight of the liquid is displaced, isn't it? Now, if the object weight is less than the amount of the water that it displaces, then the buoyant force will be more and it will float. Now, if the object weighs more than the water that it displaces, now what will happen? The density is more, isn't it? So, the buoyant force will be less and the object will sink at the bottom of the test tube. Now, I once again repeat, children. Now, we know that when an object is immersed in the liquid, it displaces an equal amount of the water, isn't it? Now, if the weight of the object is less than the amount of the water that it displaces, now the buoyant force will be more, isn't it? That is the upward direction force. Now, here you can see in the picture, isn't buoyant force is the upward direction force. Now, this will be more. So, what will happen? The object will float. Now, if the weight of the object is more than the amount of the water that it displaces, now what will happen? This buoyant force will be less, isn't it? Since the density is more, the weight of the object is more, isn't it? So, it will go deep into the liquid, it sinks. Next, we'll see what is Archimedes Principle. Now, before going into the law that is stated by the Archimedes, now considered an beaker with an side tube. Now, this is filled with water till its side tube, and a stone tied with a spring balance is immersed into it. Now, since the object is immersed into it, I said that it displaces equal amount of the water. That is, the amount of the water that is displaced will be equal to the weight of the object. So, once it is displaced, now what will happen? The water is displaced through the side tube, isn't it? And it is collected. Now, when you weigh the weight of the water that is displaced, that will be equal to the weight of the object. Now, here an upward direction force, that is vertically upward direction buoyant force will be exerted, isn't it? Now, I said that the upward direction force, that is the buoyant force, is exerted when a body is immersed in it, isn't it? Now, this vertical buoyant force will be equal to the weight of the liquid that is displaced. So, this upthrust is nothing but the force that is acting in the upward direction, isn't it? Is equal to the weight of the liquid that is displaced, or this is the apparent loss of the weight, isn't it? Now, for example, we used to draw water from the well, isn't it? Now, when the bucket goes deep into the water, right? Now you feel that the bucket that is filled with water is weightless unless it is lifted up in the air, isn't it? So there is an apparent loss of the weight in the body, isn't it? So this is equal to the apparent loss of the weight that you experience. So upthrust force is equal to weight of the liquid displaced, or that is also equal to apparent loss of the weight of the body. So now we can state the Archimedes principle. So Archimedes principle state that a body immersed in a liquid experience a vertical upward buoyant force that is equal to the weight of the liquid that it displaces. Now let's see the law of flotation. Now what is law of flotation? Now the first one is that the weight of the floating body in a liquid is equal to the weight of the liquid that it displaces, isn't it? So just now we saw in the Archimedes principle, isn't it? So the weight of the floating body will be equal to the weight of the liquid that is displaced. Now it will occupy a space when it is immersed in water, isn't it? So it will occupy the space, and that will be equal to the weight of the liquid that it displaces. The center of gravity of the floating body and the center of buoyancy are in a same vertical line. Now look into the picture, children. Here you can see that the boat is floating in the water, isn't it? Now there is a center of gravity for the floating body, isn't it? And the center of gravity of this floating body will be equal to the center of buoyancy, and this too will be in a straight line. So with this we come to the end of the chapter, children. Now in this chapter we saw what is thrust, what is pressure, what is atmospheric pressure, how to calculate the atmospheric pressure. That is, we saw the working of barometer, Pascal's law, Archimedes principle, saw about the hydrometer, isn't it? And at last the law of flotation. Now your homework for today is that you are going to learn the construction and the working of hydrometer and barometer. For barometer, you can refer page number 30 in your textbook, and for the hydrometer, you can refer page number 33, and you can write the construction and working of both the barometer and the hydrometer in your class book and submit your class book in the school office. It will be corrected and given back to you soon, children. See you in the next session, children. Thank you.